Hi guys, welcome to today's video on some periodic table trends on level 3 NCEA Chemistry. So if you find this video helpful and informative, please like and subscribe, share it to your friends who may also benefit from, who are struggling in chemistry and may appreciate some extra help. Just before we get into it, just make sure if you're someone that's year 13 and not sure what career pathway you would like to pursue, or if you want more information on certain degrees, please do check out my series of podcasts where I talk to ex-students about what they're doing at university and what it is like, how to get into certain degrees. And because you never know, because it's better to be informed now rather than half a year down the track of your first year at university later on, and then you decide that it's not your thing. Okay, so let's get into today's topic. So a few people asked me to go through the 2020 exams. I'll do that later down the track. For now, until the end of the year, I'll probably just go through particular concepts. So we are going to look at the periodic table trend. So the periodic table trend, so if you look at the 3.4 standard, it's normally broken down into three major sections. The first section is your periodic table trends and Lewis diagrams and shapes of molecules and polarity. And then the second major section is on the intermolecular forces. And the last one is on enthalpy, Hess's law calculation, and entropy. Okay, so periodic table trends is quite a big one in this particular standard, and it's actually quite straightforward once you get the hang of it. And there's unfortunately it's a lot of writing, it's a lot of rote learning, but I'm here just to make sure that you get the concepts right. So let's get started. So the periodic table trends that we focus on for NCEA level 3, we are looking at the atomic radius. Sorry, I haven't been writing for a little while due to school holidays, but my handwriting is always not the best, but just bear with me. Atomic radius, first ionization energy, and the last one is electronegativity. Okay, so the atomic radius, if you look at the word radius, it's the distance between the center of a circle to the outskirt of a circle. So which in the case of an atom, you're looking at the distance between the nucleus and the valence electrons. But because we can't see the valence electrons, so what chemists do in terms of finding out how big an atom is that they look at let's say if this is an atom, this is a nucleus. Oops, excuse me. Get rid of that. That's the nucleus. That's the valence electrons. That's a nucleus right there. That's a horrible diagram. That's a horrible right diagram, like there, and like that. There's two atoms. So because we can't see the valence electrons, so they measure the distance between the two nuclei and then divide that by 2, which gives you the rough atomic radius. Okay, but that's not the point. The point is we're looking at two major concepts that determines the size of an atom, which then determines how difficult it is to remove an electron, which is ionization energy, and also determines the electronegativity of an atom. So these are the two things that I want you to consider, especially with any of the periodic table trends questions. You need to think of these two things. One is the number of protons. Okay, so the proton number, this is quite important because this tells you how the size of the proton, the size of the nucleus, this tells you how much force of attraction is from the nucleus. Okay, so this is force of attraction from the nucleus onto the valence electrons, so onto the electrons, onto which again, if you think about the radius, how much force have you got on the valence electrons? Obviously, the more force you have acting on the valence electrons, they are going to be closer. Therefore, the atom will be smaller, but we'll get to that a bit later. Okay, so proton number, that's really important. And the other thing that we need to consider is the shielding effect. Okay, so this is probably a concept that's a little bit hard to grasp. It comes up again in your spectroscopy internal standard if your school offers you spectroscopy, but we don't really test you what shielding effect is in that standard, but it's a fundamental chemistry that explains how the technique works. But what shielding effect is, just think about your classroom. Yeah, think about your chemistry classroom. Your teachers normally stand at the front, all right, and then think of that. You think of your chemistry teacher as the nucleus, as the protons, as a positive person, as a positive charge, and then the student that's sitting the furthest away from from the teacher is a valence electron. So what is shielding effect? In simple words, shielding effect is how many layers or how many shells of electrons are there between your teacher and the person sitting the furthest away from that person, from the teacher. Okay, so the more layers there are, the more shielded that student is, because that person is furthest away, because there are more people in between the teacher and the student, which shields that person away from the teacher. So if that guy decides to, gap and run away from school, the teacher can't get him, because the people sitting in between are shielding that person from the positive nucleus. Okay, so the shielding effect, this is looking at the number of inner shells. So number of shells between the valence electrons and the nucleus. Okay, so again, I'm trying to explain this in really simple words. By definition, it's probably it's a little bit off, but you get the idea. Because the point of me doing these videos is to try to make sure you understand in language that you can relate to. Okay, so don't get like a really thick textbook and just say, oh, but you said the definition of that, and then the textbook says this. Because I'm trying to communicate in words that a year 13 every year 13 understands. Okay, so these are the two things that you need to consider. Okay, so when you look at any of these three things, any of the three trends, we need to look at, so before you decide, you need to think about how many protons they have, and think about how many inner shells there are between the valence electrons and nucleus, which determines the shielding effect. So let's look at the atomic radius. So if we go across the period, going this way, the atomic radius decreases. See, I get it wrong sometimes. Atomic radius decreases. So why does it decrease? So let's look at, why don't we just look at boron, let's look at oxygen and fluorine. Okay, so oxygen and fluorine. So oxygen has 8 electrons, fluorine has 9 electrons. So oxygen has 8, oxygen has 8 protons. Fluorine has 9 protons. So straight away, before we even consider the other things, fluorine has got a stronger nucleus. Why? Because they have more protons. That's it. It's as simple as that. And you can look at the past NCEA exam and look at the model answers. I've gone through that in my past papers videos as well. You can go through those. But straight away, the first thing you need to consider is that just look at the atomic number. The higher number means there are more protons. The more proton means there's a higher force of attraction from the nucleus. Okay, now let's look at the electron arrangement. So oxygen is 1s2, 2s2, 2p4, and whereas fluorine is 1s2, 2, oops, you love it when you write it the other way around, 2s2 and 2p5. So if you look at the valence electron, this for the oxygen, the valence electron is in the 2p subshell, and also the same for the fluorine, the valence electron is also in the 2p subshell. So these two valence electrons of oxygen and fluorine, they will experience the same amount of shielding effect. And a really simple way to put it across is that if you think about the person, like again, back to the teacher analogy, the teacher standing at the front, and then you got, our classroom, is organized in rows, right? Different 4 or 5 rows of tables and chairs. If you have, 4 people versus 5 people, and 5 people sitting in the same row, they are technically experiencing the same amount of force from the same amount of attraction from the teacher, because they're sitting approximately the same distance. So there's no actual shielding effect because they're sitting in the same row. So there's people, the number of people sitting between the teacher and that group of students will be the same because they're sitting in the same row. Okay, so combining the two effects together, and this is something that a lot of students use but don't understand what it is. So once you consider, yep, this one has more protons, yep, we know this. That means you have so fluorine has more protons, So fluorine has more protons, so that means it has a stronger force of attraction from the nucleus. And then the valence electron have the same amount of shielding from the inner shells because the valence electrons are in the same sublevel. So what does that mean? Combining these two effects together, that means the valence electrons of fluorine will experience a greater effective nuclear charge. And it's just a fancy word of just saying, okay, so the protons, the force of attraction from the protons minus the amount of shielding equals how much force of attraction these valence electrons are actually experiencing. Okay, so that's what I tend to tell my students. Think of effective nuclear charge. So it's kind of like, yeah, there's so much force of attraction coming from the nucleus, but only a certain amount actually reaches the valence electrons. So those are actually effective in terms of holding on to the valence electrons. So the valence electrons of fluorine receive greater experience. Receive is probably not a good word. Experience a greater effective nuclear charge. So in less scientific words, so what does that mean? That means it's pulled in closer. All right, it's getting more force of attraction from the nucleus, so the valence electrons are pulled in closer. So if the valence electrons are pulled in closer, doesn't that make sense that the atom is smaller? Because remember what we are measuring? We're measuring the distance from the nucleus to the valence electrons. And if the valence electrons are experiencing more force of attraction, hence they get pulled in closer. Okay, so let's just do that. All right, so they're pulled closer. They're pulled in closer, and that means they are smaller in terms of an atom. Okay, so that's what that's what atomic radius actually talks about if you're going across the period. Okay, so if you go across the period, the atomic radius normally decreases because as you go across, the number of protons increases, so there's more force of attraction from the nucleus. But because the shielding effect is the same for the valence electrons, because if you can write down the valence you can write down the SPD electron configuration for all of these elements in the same period. But if you someone that's understand chemistry, you know that the first period, this is period 1, period 2, period 3, period 4. So what that means is that they will have the valence, if they're in the same period, that means they have the valence electrons in the same energy level, so there's no extra shielding effect. Okay, so that's how it works. Now just I'll talk about ionic radius a bit later, but let's just quickly, so I spent a lot of time doing across, let's just quickly talk about going down. If we're going down, the atomic radius increases. Now I'm not going to write this this whole chart again, but again you need to consider proton number and shielding effect. So let's really quick, let's do Na. So what should we do? Let's do Na versus K. Okay, so Na versus K. Na is 11, K is 19. So this is 11 protons, 19 protons. So straight away you can talk about, yep, potassium has 19 protons, therefore has a stronger force of attraction from the nucleus because there are more protons. All right, so that's correct. But what happens now is that you need to look at the electron configuration. So the valence electrons, one is in the 3 energy level number 3 in the 3s subshell, and then for potassium the valence electron is in the 4s subshell. So for your potassium, this has more protons, but this is outweighed by the valence electron in the higher energy level. The valence electron in higher energy level, and what that means is that it experiences more shielding. It has more shielding from the inner shells. So this more protons is not as significant. When you're going across the period, the more protons is more significant because the shielding effect is roughly the same. But when you're going down the group, the more protons, yes, you still have more protons, but this more protons become far less significant compared to the shielding effect. So combining these two together, so if you look at potassium as an example, yes, there are more protons, but this is not really significant. There's more shielding effect. So as a combination of these two effects together, the valence electrons of potassium, the valence electron of potassium would experience less effective nuclear charge. Less effective nuclear charge. And as a result, they are bigger. Atomic radius is larger. Why is it larger? Because you're experiencing less force of attraction, so obviously the valence electrons are on the loose, therefore they will tend to be further away compared to the sodium's valence electrons, so the atom is larger. Okay, so hopefully that makes sense. So that's atomic radius. Now, if you understood that, and it's really crucial that you understand atomic radius, because if you understand atomic radius, you can understand the other two really easily. Because what is the ionization energy? Ionization energy is the opposite of atomic radius. First ionization energy, by definition, is the amount of energy required to remove one valence electron from one mole of atom at its gaseous state. Okay, so it's looking at how you can think of ionization energy as I want to remove an electron from an atom, and if there's more force of attraction between the nucleus and the valence electron, if that force of attraction is quite strong, doesn't it make sense that you need more energy to separate them? So if you think about, let's go back to the atomic radius. Let's say if we look at the let's say if we look at the first ionization energy difference between iodine and fluorine. So if we know that fluorine has more protons and the same shielding, blah blah blah. So if we know the valence electrons of fluorine experience greater effective nuclear charge because they're pulled in closer, doesn't that make sense? I'm going to use a different color pen. Doesn't that make sense for your ionization energy? Is that more energy is required to actually separate this particular force of attraction. Okay, so for your first ionization energy is more, you need to have more energy to actually break this force of attraction. So for your ionization energy is the opposite. Your first ionization energy increases as you go across a period, and your first ionization energy decreases down the group, because it's the opposite of atomic radius. Okay, so this is what I meant. It's all about rote learning, trying to, memorize a model answer and get excellence in the exam. Yeah, that's important, but you have to understand, because rote learning and memorizing can only take you so far. Okay, so especially when we do later on, when you do other standards, there will be less and less rote learning. It's more of understanding. Okay, when you do organic, when you do aqueous, it's more about understanding. So start to train yourself this way. Okay, so just think about atomic radius decreases. Yep, the atom is smaller. Why is it smaller? Because there's a stronger force of attraction from the nucleus and the valence electrons, so they're pulled in closer. So what if I want to take an electron away? So I have to overcome that particular force of attraction, and if that was really strong, I will need more energy. So ionization energy is the opposite. Okay, now electron negativity. Electron negativity is looking at the force of attraction between the nucleus and the bonding electron. So it's actually really similar to atomic radius. And if you forgot how to do electronegativity trend on the day, just remember fluorine is the most electronegative. Fluorine is the most electronegative. So if you're going towards it, the electronegativity increases. So let's use a different color pen. So as you're going from left to right across a period, the electronegativity increases, and also electronegativity decreases. So it's the same as your ionization energy trend, but it's different. Okay, because what's the electronegativity? Electronegativity, like I said before, is measuring how the force of attraction between the nucleus and the bonding electrons. So it's how much, how much do they want an extra electron? You can think of it that way. If you were what is electronegativity? You know, how we look at the electronegativity difference, you know, to explain polarity. So it's like you and your siblings, you really want to buy a gaming console. For example, you want to get a PS5. But you are the main person, you play most of the time, but you know, your sibling plays a little bit, so you're technically sharing it, but because you're more electronegative, you know, you want it more, so you get a share. It's uneven sharing, okay? So you play a little bit more. But why does it do that? So what is the difference in terms of electronegativity? Is the force of attraction from the nucleus to the bonding electrons. And what determines that? The number of protons from your nucleus, because the more nucleus you have, the more protons you have, the stronger force of attraction you have. And it also depends on where the bonding electron actually goes. If you're sharing electrons in a energy level that is similar, let's say if you compare oxygen and fluorine, if you compare their shielding effect, it's roughly the same, because they are in the same period. They have the valence electrons are roughly in the same proximity from the protons, so they experience the same amount of shielding effect. But because fluorine has more protons and really just needs one more, so it has a high electronegativity. Okay, so that's a general trend. Electronegativity, I think if you understand, as you can clearly see, I spend a lot of time on the atomic radius, because if you understand the radius, you understand ionization energy, because it's the opposite. And then you understand electronegativity, because it's the same concept. You're looking at the force of attraction, shielding effect, and you just need to combine those two together and ask yourself, okay, so which one outweighs the other, which one's more significant, and what is the result after that? Okay, now just last bit that I do want to quickly talk about is the Ionic Radius. Okay, because this sort of question normally comes up as well. Let's say, for example, fluorine versus fluoride, and then magnesium versus Mg2+. And this is what I always suggested my guys to do. Always write down the proton number and the electron configuration. So for this is 9, so this is 1s2, 2s2, 2p5, this is 2p6. So let's just look at the left hand side for now. So this has 9 protons, this has 9 protons, and the reason why I need to exclusively explain this, because this is different sort of concept involved when we took compared to what we talked about just now. So yes, the protons is roughly the same, so the force of attraction is the same, and the shielding effect, you're adding an electron. So in fluoride, where did the minus go? In fluoride, you're adding an extra electron, but that's going into the same energy level. So the shielding effect is still roughly the same. But if you actually look at the size, if you actually Google the sizes, if you look at fluorine and fluoride, bromine, bromide, chlorine, chloride, iodine, iodide, the difference between the sizes of the atom and the ion is so significant that the ion, like the negative ion, are sometimes almost twice as big as the atom, just because of that one single electron. Because what is the fundamental, what is the contributing factor here is the electron repulsion. Okay, because you added an electron. And electrons are negative. So what that means, you introduce another negative charge, and that completely changes the whole dynamic within the atom. Because before the 5 atom, electrons were like just hanging out in the 2p subshell, but then you added another one, and then they will be like, oh my god, a new negative charge, we need to get away from each other. So they start taking up more space, they expand, they try to become stable, and then they try to stay the heck as far away from each other as possible because of this new additional electron. So that is the contributing factor here. Okay, whereas you look at the positive ion, if you look at the magnesium versus Mg2+, the atom versus the positive ion, this is again, this is 12 protons, so the protons is the same. This is 1s2, 2s2, 2p6, 3s2. This is 1s2, 2s2, 2p6, because you lost 2 electrons, yeah? Mg2+ lost 2 electrons. So the number of protons is still the same. So the force of attraction from the nucleus, again, is still the same. That doesn't change. But what has happened is that if you look at the Mg2+, you lost an entire energy level. You lost the entire energy level. So there's the shielding effect is completely different. So there's actually two things. So first of all, there's less repulsion between the electrons because you have less electrons. And second is that you have lost an entire energy level. So your valence electron is now in 2p, whereas before the valence electron is in 3s. So you lost the entire energy level. So there's less repulsion, and there's also there's less repulsion between the energy levels, and there's also the less shielding effect. There's more shielding effect. What am I talking about? There's less shielding effect, so there's more force of attraction. There's less shielding effect on the Mg2+'s valence electron. So if there's less shielding effect, obviously the new valence electrons would experience more force of attraction. So as a result, they'll be pulled in closer, and as a result, Mg2+ is smaller. Okay, so in this case, F is a lot smaller than F-. In this case, Mg is a lot bigger than Mg2+, and this applies to all of the ions. Your cations, which are your positive ions, are always smaller than your atom, and your negative ions, which are your anions, they are always bigger than the corresponding atom. Okay, so hopefully this video helps you to understand the concept. But at the end of the day, if you want to do well for the externals, I strongly recommend you to grind the questions. And if you look at the past 5-6 years questions, it's all the same. Just getting the right words. Be very careful with the choice of words, but you need to first of all understand it, because if you don't understand it, you can memorize the answers all day long. But if we give you something new, I'll give you another example since there's a bit of time. Let's say if I'm being really nasty, I give you Na plus and F minus, right? And I go, which one's bigger, which one's smaller? And then if you don't understand, you look at this like, what the heck? And my teacher never taught me this. All right, this is not part of the course. But if you actually look at this has 11 protons, this has 9 protons. What is this Na plus electron configuration? You lost electrons, so it's 1s2, 2s2, 2p6. What's fluorine's electron configuration? You gain the electrons, so it's 10 electrons, 1s2, 2s2, 2p6. If you look at that, it's the same electron arrangement, so they have the same shielding effect, but if you look at the proton number, the Na plus has more protons. So because Na plus has more protons, there's a more force of attraction coming from the nucleus, and the shielding effect is exactly the same. So the effective nuclear charge that the Na plus's valence electrons experiencing is going to be a lot stronger. Therefore, Na plus as an ion is going to be smaller than F minus in terms of the size. And if you look at the first ionization energy, how much energy, so size-wise, radius, Na plus is smaller, but then if I were to remove an electron from Na plus, and they will require more energy to do so. Okay, so hopefully this is helpful enough. So my aim for the rest of the holidays, school holidays, is I'll try to cover all the main concepts. I already done Hess's law previously. I will do so I'll probably do shapes of molecules, and then do intermolecular forces, and then do a bit on entropy. Okay, so hopefully you found this video helpful. Sorry, it's a bit of a long one, but if you enjoyed it, give it a thumbs up and subscribe, and share with your friends who need some help in chemistry. So like always, take care, and I'll see you guys next time. Bye bye.